Welcome to this NPTEL lecture on antennas. Now, we will see today some advanced topics. The first we will see array pattern synthesis. Actually, we have seen array antennas, but we have seen only one dimensional antennas. Today, we will first see the two dimensional antenna and then see that there is a need for having a synthesis procedure in antenna, array antenna design. So, that we will try to see, though we will not go very deep in that, but just I will sketch that whatever you learned. If you want to explore that antenna synthesis problem, you can go with this background. Okay, so, first let us consider a two dimensional array, because we have not considered that. So, you see a two dimensional array. For simplicity, I have taken that it is a one dimensional array in x axis and also in the z axis. This one dimensional array is repeated. So, I am considering that as before n plus 1 element along x axis. Now, today there are such m plus 1 number of such linear arrays. So, total elements are n plus 1 into m plus 1. Okay. They are uniform spacing, that is why uniform array, and also the excitations are there are same excitation. So, we can this array may be described as an array of m plus 1 linear arrays. Thus, by using the principle of pattern multiplication, the two dimensional array factor will be the product of the array factor for m plus 1 linear array along the z axis with the array factor for the n plus 1 elements arrayed along x. So, we can write the array factor since it is two dimensional. So, we are writing explicitly the psi angle that we are expressing in terms of theta phi. Khali name. Where you can note that we have used this, that AR cross AX is sin theta cos phi and AR cross AZ Now, as before we generally go to the U plane. So, here since it is two dimensional, we will introduce the two quantities u and v. So, u as before we will write as k 0 d sin theta cos phi, and u 0 is alpha d, and v we are introducing as k naught d cos theta, v naught is beta d, and so we can rewrite this array factor, two dimensional array factor as I naught So, this array factor has its first principal maxima when u is equal to minus u 0. So, first principal maxima when u is equal to minus u 0, v is equal to minus v 0. So, in that direction it has the maximum radiation, and if we take alpha is equal to 0 is equal to beta, that means the progressive phase shift, then this direction will be perpendicular to the plane of the array, that is along plus minus y direction. For suitable values of alpha and beta, the beam can be directed in any direction. So, this is called the concept of phased array, that if I want to move the beam, that can be done by putting some values for alpha beta. So, whatever in which direction you want to put, based on that alpha beta can be put the values. So, since this is done electronically, that is also called electronic scanning. In the case of a broadside array, the angular width of the lobe in the x, y and y z planes is obtained by setting n plus 1 by 2 u is equal to plus minus pi, and so this is in the x y plane, and in the y z plane m plus 1 by 2 v is equal to plus minus pi. So, the same that we have done for linear array. So, it can be easily shown that bandwidth beam width in the x y plane is given by 2 lambda naught by n plus 1 d, and beam width in the y z plane is. So, in both the cases you can see that as the case for broadside array, the beam width is this is the null to null beam width, this is inversely proportional to the array length in that axis. In a similar way, the half power beam width can be shown to be that beam width 3 dB in the x y plane, that will be 2.65 lambda naught by n plus 1 pi d, and beam width 3 dB in the YZ plane, it will be 2.65 lambda naught m plus 1 pi into d. Now, from this we can find out, since we have in two planes we have the beam width. So, directivity can be obtained, and please note that there are two beams. So, directivity will be 4 pi divided by 2 into bandwidth 3 dB, that x y into beam width 3 dB into y z. So, that if you do it comes to 8.83 n plus 1 m plus 1 d square by lambda naught square. Now, we can say that n plus 1 into m plus 1 into d square, that is the area of the whole array. So, 8.83 area by lambda naught square. The same thing, that physical area as a electrical or in terms of wavelength, that means the electrical physical area into the some constant term. So, that is directivity is proportional to the area measured in wavelength squared. So, this is a general property of area antenna. So, in this case also that came. Now, the question is that this is two dimensional array, that time we have not covered, but in general two dimensional arrays are common. If you want to have a phased array, it is better to have a two dimensional array. Now, we will again go back to the linear array and we will see some interesting results. So, let us see the array factor for an equally spaced uniformly excited linear array. For we will see few array numbers. So, here let us say that we have 3 element array. This is the array factor turns out. Here it should not be psi, actually it is u, f u, u versus u, please correct it. It is wrongly written, because we are, our thing is u, or you can say function of u plus u 0, and this is u plus u 0. So, that axis. So, this is for a 3 element array. Then if I do for a 5 element array, n is equal to, again it is not n, n plus 1 is equal to 5. So, you see this is the array factor. So, compared to the previous one, you can see that we are having the, let me show the previous one, compared to that the n is equal to 5, the beam width is reducing. If I go to n is equal to 10, beam width is reducing, but also you see that number of side lobes are also increasing, and this. Now, from these 3 graphs, I am again showing this, we can draw several conclusions. The first one is that as n increases, n or n plus 1, in our case we are considering n plus 1 always odd number, because we are placing a central element at the coordinate of our array thing. So, as n plus 1 increases, the main lobe gets narrower. So, this is one of the observation for an uniform linear array, it is always true. Now, again if n plus 1 increases, the number of side lobes also increases. But how many? Can we say that? Yes, we can say that number of full lobes means number of full lobes means one main lobe plus all side lobes. In number of full lobes in one period of F U one period of F U that equals n, where n plus 1 is our element number. That means, if I have 3 element array, I should have 2 globes. You see, 3 element. So, this is one full lobe, this is one, so 2 lobes. Go to 5. So, we should have 4, 1, 2, 3, 4. 10, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, this is a general thing that number of full lobes will be n if we have n plus 1 element array. Now, the fourth property is that, or this is third property, is that the minor lobes, if you calculate, it will be minor lobe width is 2 pi by n plus 1, and the major lobe or the grating lobe, both major lobe or main lobe and grating lobe, major lobe as well as grating lobe width is double of that, is 4 pi by n plus 1. So, you see that total how many things? So, I have 2 pi into n plus 1 into, can I say that, n minus 1 side lobes in a period, because I said total n full lobes. So, n minus 1 side lobes 1 plus 4 pi by n plus 1. What is this? You can take 2 pi by n plus common, that gives you n minus 1 plus 2. So, it is n plus 1, so it is 2 pi, and we always say that f u is a repeats periodic function with 2 pi is the period. So, this is also one interesting thing. And the fourth property is, what is the side lobe level? We have already defined side lobe level in the basic parameters, that is the maximum value of largest value side lobe by the maximum value of main lobe. So, as n increases, this SLL decreases. So, if you calculate, then for n plus 1 is equal to 5, we get SLL is minus 12 dB, n plus 1 is equal to 20, SLL is minus 13 dB. If you have larger than this, SLL will approach the value that we have already derived, 13.3 dB, or roughly we call it minus 13.5 dB. So, side lobe level cannot be put below minus 13.5 dB by an uniform array. Also, there is another property that you can easily prove, that F u is symmetric about pi. this thing you can see that if this is pi, you see this is symmetric, this point is I think pi, then this point is pi, you see it is symmetric, this point is pi, you see it is symmetric, also it is periodic with 2 pi. Now, the question is actually these properties are interesting, but this is actually a drawback, because you see that if I have an uniform array, I cannot put side lobes at my specified values. Suppose in some application if I require it to be 20 dB, I cannot do, and in radars in various applications we require it to be much lower, and also we want that the you see the gain also, the directivity is also fixed for linear arrays. It is inversely proportional to the given array length, but it cannot be changed. So, that actually puts a bottleneck that okay, we can get it. So, we will have to have more elements to decrease the value, but then the problem is that size may not be available, so much array length may not be available for an antenna, and also if I want to increase the number of elements, then the element spacing, because already there is an restriction on element spacing that I cannot go beyond lambda naught by 2. So, if I want to put more number of elements, I will cross that and I will invite grating lobe, which is again not desirable. So, actually you see there is nothing to do from our side much. As a designer, we do not have much to do if we choose an uniform array. So, that is the motivation for going to that, can we synthesize any given pattern. Suppose someone wants some exotic pattern, suppose I want fu by u, in many cases we require fu by u to be like this. This is called sector beam, that in a particular sector I want uniform, outside that I do not want, but that type of thing, is it possible? Or someone might say that I want that I do not want any side lobe, or I want side lobe to be very small, I do not care about what is the directivity. So, these things are not possible with an uniform array. Always there will be side lobes, always there will be that throughout the whole space the beam is extending, may not be the main beam, but the other beams they are always radiating. So, from that place if there is a strong interference that it will pick up, a strong noise that it will pick up, etc. So, this is the motivation for going to array pattern synthesis. But before going there, I will see, if you see my earlier array antenna things also, there is one thing that I always express the array factor as fu by u. Now, u, what is u? U we have defined as k naught d cos psi plus alpha d, or I will plus u naught, where u naught is equal to alpha d or beta d as the case may be. That means the progressive phase shift, etc. Now, this is a constant in a particular case for anything. The point is, you see this u, what is the physical significance of this u? The significance of psi we have seen that if I have an array axis, this is my array axis and my observation point is here, the solid angle that the observation point's radius vector makes with the array axis is psi, angle psi. That was our thing, but if I have the array axis as a particular x and y, then I know that what is the value of this psi in terms of theta phi. But what is the physical significance of u? Actually, there is no physical significance of u, but it is very easy to understand this whole array theory in terms of this fu function, because this becomes very simple, that sinc type of function it comes, that is why I do it. But now suppose I got a pattern, array pattern function, now can I go back to the physical significance? That means, if I want to see that in theta plane or phi plane how it looks like, so that means we generally want radiation pattern of this array factor to be in the polar plot. So, how to do that? That we will now see. So, in this lecture we will see, suppose I have a fu something like this, that this is my u and this is my, I am taking the mod. So, there is no negative term. I am arbitrarily drawing it. This is arbitrary. So, this should be symmetric. So, here then suppose this is my main beam I am getting. So, obviously, main beam always we get at a point where the sin u plus u naught, that is should be 0, that means at minus u naught. This is always true. If for a broadside array this u naught is 0, that is why it comes here for an parallel. So, this is a general thing. So, this is my 0. Now, the first task is to put where is the, let us say that we are talking of x axis array, which we did for our linear array. So, first let us put that actually this relation you see u is equal to k naught d cos phi plus u naught. Now, this cos phi can be, in case of any particular axis, this will be replaced by u is equal to k naught d cos theta, let us say, plus u naught. Now, what is actually, this is the transformation relation. That means, I want it in place of theta u. You see, I have written this because cos psi, actually it is k naught d cos psi. Now, that psi in a particular case will take the form of either sin theta cos phi or cos theta something. Now, so this is a physical thing. Now, theta can, suppose we are looking at that we want the thing that in the phi, a fixed phi plane. So, theta is a physical thing, it is the elevation angle, that means with the axis you see. Now, what is the theta? Theta can vary from minus pi to plus pi. So, what will be the visible space? Visible space is in the u plane or in the u variable, the visible space will be from minus k naught d to plus k naught d. So, first in this pattern I will have to locate that. So, let us say that arbitrarily this is my, arbitrarily I am saying because this pattern I have done here. So, first I will have to locate the thing, maybe it will, so this value is then k naught d, theta can actually in our coordinate system theta is 0 to pi and phi is 0 to 2 pi, sorry. So, if it is 0 to pi, then what is the value when theta is equal to 0, then u is equal to k naught d, first, so let me write theta is equal to 0, u is equal to k naught d plus u 0, and when theta is equal to pi, u is equal to minus k naught d plus u 0. So, basically I will have to locate that this is my k naught d plus u 0, this is my, let us say, minus k naught d plus u 0. Okay. So, this is my visible space I want. So, then if you look at this expression u is equal to k naught d cos theta plus u naught, can I say that in the theta plane or in terms of theta, this is an equation of a circle, u minus u naught is equal to k naught d cos theta. It is a nonlinear relation, but it is an equation of a circle. So, the next thing I will have to do, I will have to draw a circle. I will have to draw a circle. Where I will draw the circle? The circle will be centered at u naught. The circle will be centered at u naught, and the circle's radius, the radius of the circle, that will be n plus 1 by 2. So, radius is n plus 1 by 2 k, what I will call k naught d. This is the radius, center is minus u naught. So, this is a circle, and this circle you will see extends this whole visible space, because I have taken this k naught d, you see minus k naught d. So, this is represented. Now, any point you want to put there, what you do, you see that suppose this is u plane. So, you draw the visible, always this circle will be covering the visible region. Now, you suppose, actually let us again come here, suppose I want what is the value of this point. So, what I will have to do from here, I will have to put a vertical line, that line will intersect some point at this circle. Now, from the center you draw and connect this intersection point, and now from this plot you find out what is this value in this scale. Now, in this line you plot that, maybe it is, let us say 2 dB. So, it will come here. So, this is a point on the final polar plot. Similarly, this point, suppose it will come here. So, this point may be here, this point let us say here. So, it will be somewhere here much lower. So, you see that finally, when I take this plot, it will be something like this. So, every point now you make and then take a locus of that, that will give you the polar plot, as this fellow is doing. You see that main beam is here, in the u plane it looks that it is in the center, but actually if you put, you see the beam is tilted, actually the beam is like this. So, this point will correspond here. So, this intersect, and then from here the value we put, and that point is here, that point is here. Similarly, this point he has put here, but the value is actually here. So, this point he has connected like this. So, finally, this locus is the polar plot. So, this is the technique that should be used, because this transformation actually demands this. So, by that now you get a physical insight that okay, where is the beam, etc. So, with this I end this discussion. The next lecture will go to that what is the synthesis, how to do the attempt the synthesis procedure, that we will discuss. Thank you.